Yeah, indeed. So since we have no discussion session today, you are encouraged to ask me questions during the lecture. So don't hesitate to interrupt me and so on. So we stopped at the point where we introduced the linearized gravity, basically. Okay, there were some questions. So let me just copy the thing. So there was so we were discussing linearized fluctuation of the small fluctuation of the metric, which allowed us to do expansion in this small fluctuation. Okay, so the weak field approximation in and so at the linear level, we decided that there was a simple equation for this linearized fluctuation was had a form which was okay. There was the 16 pi g Newton, okay, but then there was a tensorial structure of the source of the following sort, okay, and T notation is simply a trace of the energy momentum tensor. Okay, so basically this equation tells us this is a perfectly solvable and invertible equation, and so this equation shows us what is the fluctuation of the metric in the weak field approximation, linear approximation. What is the fluctuation of the metric produced by a source? Okay, so we have a source which we call T mu nu, the source with energy momentum T mu nu, and the source and there is a response from gravity. So H mu nu is response from gravity. So gravity responds by producing a non-trivial metric, non-trivial gravitational field. Okay, so schematically we can write it like this, and so the corresponding response is given by expression. So let me put this. Okay, it doesn't matter. So let me put that in. Okay, so this is the response, and the meaning of 1 over box is it's a Green's function, right? So, or we can write it as so this is at point x prime, and let me call it G, a propagator of the graviton. This coupled with a source alpha beta, and I can I can put this separately here. Actually, I can also rescale it into the propagator. So this is evaluated point x prime. So where G mu nu, this is a graviton propagator, okay? So which has a tensorial structure that leads effectively to this expression, and tensorial structure we can write it as mu alpha, mu beta symmetrized. Mu alpha minus 1/2 of eta mu nu at alpha beta box. And so this is a Green's function, and which also is related in with the Feynman propagator of the graviton in the quantum theory. Of course, in that case, we have I epsilon prescription for the going around the contours. Okay, so basically, now we have this response of the gravitational field. Okay, so we have a source. A source creates gravitational field, and now we can try to understand how this gravitational field influences a probe energy momentum tensor. For example, source could be some heavy object, let's say a sun or a star, and so we want to understand how this influences the propagation of a planet with smaller mass, which we can treat as a probe. So we can introduce additional energy momentum tensor and try to understand how this, so energy momentum tensor of a probe, let me call it tau mu. Okay, so this is a probe, and the probe will be affected by, due to the fact that a source modifies gravitational field. Okay, so how it will be affected? So it will be effective action of the probe in the background of this gravitational field. Created by the source. Okay, so this is the structure. But now, taking into account this form of the probe, of the gravitational field produced by the source, we can see that this is effectively reduces to the following expression, right? You can also think in the following way, which is so in other words, and let's say 16 pi. Okay, 16 pi's we have. We didn't absorb in the. We have it here. I don't know why I'm carrying the 16 pi's around. What is important is the power of G Newton. So what is important is that this is linear in G Newton. Okay. So basically what we are observing is the following thing, right? That there are two ways to look at it, at least two ways to look at it. So we can look at it as in fully classical language, as we have a source, T mu, and this source produces a gravitational field, classical gravitational field, and this classical gravitational field, H mu, perturbation of the gravitational field, of course affects the source, all the sources with energy momentum tensor tau mu, a probe source. Or we can understand this as in the language of one graviton exchange, okay? Because what is this? This expression is one graviton exchange between a source and a probe. Okay. Now the language of one graviton. So notice the following thing: that the language of one graviton exchange is fully quantum. It can be fully quantum. In other words, as a exchange, I can use fully fledged correlator Feynman propagator for a quantum graviton field. And nevertheless, I will get exactly the same answer among two classical sources at the level of one graviton exchange. At the level of one graviton exchange, this will reproduce linearized, classical linearized dynamics of Einstein gravity. Okay. Now this is pretty generic. The same happens. You probably remember from QFT classes that the same happens for the Coulomb law. You can understand Coulomb law as one photon exchange, but at the same time, we can also understand Coulomb law by solving simply classical equation for classical Maxwell equation for the point-like source. Okay, so this is generic, this situation. By the way, this is also, you can take this as an indication that quantum gravity works. In other words, at the linearized level, fully quantum consideration of one graviton exchange, quantizing graviton field, writing down graviton propagator at one graviton exchange level, this reproduces classical linear gravitational field among the two probe classical sources. Okay. As I said, please interrupt me anytime during the lecture. If there is something that you don't like or you see some logic gap, we'll fill it immediately. Try to fill it at least. Okay, here is a question.
Now, the thing is that seems you said that in principle this tells us that gravity can be, this exchange can be considered, sorry, this interaction can be considered as a one graviton exchange, but isn't it better to interpret it that, let's say, 3-level QFT is simply equivalent to classical differential equation resolution? I mean, what I'm trying to say is that,
yeah, that's
that gravity.
Okay. Yeah, that's a good point. Yeah, that's a good comment, and that is an important comment to clarify. So the question is, actually the comment is about correspondence between, when we say at the level of QFT, what classicality means, okay, at the level of QFT. And so here the comment was that 3-level, and so the correspondence between classical and the 3-level. Actually, that's not completely true, okay? So, and this is important to understand that 3-level means, to fix terminology properly, 3-level means that we don't have loop diagrams, okay? So 3-level processes by, let's say, graviton scattering, all right? All possible processes like that. This is a 3-level process, okay? Or even this, graviton scattering. This is a 3-level process. Let's say I can look at the fully fledged quantum S-matrix process in which I have 2 gravitons in the initial state, 2 gravitons in the final state, and ignore loops and compute it in the three approximation. Okay, so for example, this will be 2-2 graviton scattering in 3 approximation. There will be other diagrams that will contribute, for example, diagrams like this, and so on. All these are 3-level, but this doesn't mean that they're classical. In fact, there is absolutely no way to understand classically state of 2 gravitons. 2 graviton state is an intrinsically quantum state because it contains too few occupation number of quanta to be treated classically. So therefore, classicality and 3-level is, we have to be very precise when we're trying to make correspondence. In other words, the classical exchange, okay, of graviton, 3-level exchange of graviton, when it gives a classical result, for example, diagrams like this. Remember, I drew yesterday the correction to mercury perihelium, for example, in the diagrammatic language. 3-level exchanges, when there are no quantum graviton states in either initial or final states, even if the story is 3-level, okay? So here, in this example that I considered, we only had intermediate graviton exchange, okay? So graviton here appeared only as a intermediate, a virtual particle. There was no graviton in the final state. And so in this case, the tree level, yes, recovers the classical result, but this should not be taken as a fact that any tree level process is classical. No, that's not the case. Here I'm giving you an example. Then if there are quantum gravitational states, quantum graviton states, either in initial or in final states, or if there are any loops, for example. So loops are not tree level, but tree level, even without loops, if there are some quantum graviton states, either in initial or in final state, that cannot be understood classically. There's no way to understand classically scattering of two gravitons into two gravitons. No way. Okay. So, and this is very important. Does this answer your question?
Yes, 100%. Thank you.
Okay. Very good.
Sorry, Gia, can I ask you one thing regarding this?
Yeah.
So what state can be thought as classical? Is this a current or something that is conserved that can be considered classical initially and final state?
Well, classical states, as I said already, in there was a question. Remember yesterday about the classicality quantum story. Now, in general, in quantum field theory, so if we really want to start from scratch, quantum field theory, and then describe nature, and nature is quantum, we know there are no truly classical states in nature. Even stars and Earth and the planets, and at the end of the day, they are quantum. However, of course, we know that they are among all possible quantum states of nature. There are certain states that are well approximated classically, right? So the general rule, the states that are well approximated classically are the ones which have high occupation number of quanta, okay? So for example, but of course, high occupation number of quanta has to be within the relevant scale. So for instance, imagine I'm looking for a problem at some length scale L, okay? And I have sources that are relevant for this problem. And these sources consist of, there are some sort of wave packets or solitons, which I can treat classically. Of course, in reality, they are not classical. They are certain occupation number of quanta. But the bottom line is that if occupation number of quanta of the wavelength L is much larger than 1, then up to corrections of 1 over NL, these sources can be considered as classical. So this is basically the definition of classicality, right? So in that sense, and we said yesterday, if I have a quantum field, doesn't matter what spin, the connection between quantum field is essentially, this is an important factor. This is H bar. And this is what we should remember, H bar over volume and the occupation number, okay? The expectation and the occupation and the creation operator, right? Operator. So therefore, we know that then the classical field effectively is this object. Sorry, let's call it N capital. Okay, so this is the important dictionary. So dictionary is that the classical field is H bar times N divided by V, which means that this is like just number density, or we can write it as H bar times number density. Okay, number density is N divided by V. So basically, classical field is essentially a square root from H bar times the occupation number density. And now we can decide in what approximation we want to treat our field classical. So classicality, if I set in the units when H bar is 1, classicality means N being much larger than 1, okay? But of course, classicality is never exact, only at infinite N. And correspondingly, there are always corrections to classicality, which go as 1 over N, okay? So that's a simple rule. This applies to arbitrary operator, expectation value of the operator, current, etc. So that's a simple rule. So does this answer your question, or you meant something
Yeah,
different?
perfect. Thanks a lot. Sorry, I missed it
Okay.
yesterday.
Okay,
Thank you.
thank you. Okay, so very good. So now let's. So I'm structuring this discussion in the following way, right? So we had linear gravity, okay, linear theory of massless spin 2, and I said that a priori you can go top down, start from Einstein, linearize it, but the great thing about theory of spin 2 is that actually you can also start bottom up. You can simply ask the question, I want to construct a linear theory of spin 2 massless. What is it? And that theory coincides with linearized Einstein. And as we said yesterday, the reason is that only the gauge invariant configuration of those different possible two derivative terms, only the gauge invariant configuration is the one that allows to eliminate unwanted degrees of freedom, which leaves only 2 propagating degrees of freedom. Any departure from that structure, okay, from any reshuffling coefficients, relative coefficients, of course, overall coefficient we can always absorb in redefinition of Newton's constant, but any reshuffling of relative coefficients among different terms will generate physical, pathological degrees of freedom. And so this is the power. On one hand, you can think of it as a power of gauge redundancy. And on the other hand, we can think of it as a power of high spin considerations. In other words, theory of spin 2 massless is unique. And that's Einstein, okay? Now, of course, we can trivially add new degrees of freedom. That's a different story. But if you want to have a theory of massless spin 2, that's Einstein. So now we can go. So now I will structure discussion in the following way. First, I will discuss canonical normalization. So how to go from linear theory of metric perturbation to a canonically normalized graviton, because this is important. And then we include nonlinearities, okay? So metric perturbation that we considered so far, this h mu nu, this is dimensionless, okay? So it does have dimensionality. So if we wrote the theory of this metric perturbation in the following way, if I reconstruct theory from the equation, the theory, the action would be d4x, and then there would be 1 divided by Newton's constant, and h mu nu linearized tensor. Okay, I'm ignoring coefficients, factor of 2s and pi's. And then there was a coupling of this h mu nu metric perturbation to different energy momentum tensors. For example, we had a probe and the source and so on. Okay. So this was the linear theory, and now h is dimensionless. Correspondingly, Einstein linearized tensor that we had, this contains 2 derivatives. So this has dimensionality of mass square, right? And so h is dimensionless, so we have Newton's constant here, 1 divided by Newton's constant, okay? Which in h bar, here I wrote it in h bar equals 1 units, okay? So the field, so therefore h mu nu is not a canonical normalized field. Now, in order to go to a quantum theory, one thing we need to do is to normalize field canonically. Why is that necessary? Because without canonical normalization, we have to agree on a norm. Because if we don't agree on a norm, then I cannot really understand. If you tell me you have a field and the coupling of that field is 1 million, I will not be able to really understand whether the theory is strongly coupled or weakly coupled, because we have to agree on normalization. Okay, so we need a reference point. And canonically normalized bosonic field, okay, has dimensionality of mass. Okay, because canonically normalized bosonic field of a boson, right? Action of a boson is d4x, derivative square. Okay, so canonical normalization of boson, dimensionality is mass. Okay, as dimensionality of mass. So correspondingly, we have to canonically normalize this field. Now, so we have to absorb 1 over g Newton into the redefinition of the field, and correspondingly then g Newton will appear here, okay? So what will happen is that, so but instead of g Newton, now it is useful to go to the Planck mass, okay? Now remember, we introduced a Planck length in the, I think it was in the very first lecture. So let me restore h bar again. So I'm keeping c equals 1 all the time, but h bar sometimes is useful to restore, as I said. So the definition of Planck length square is h bar times Newton's constant, okay? So this is the length scale. Now this length scale for the values of Newton's coupling and Planck constant that we have, we can express, for example, in centimeters, and it is an extremely small length scale, extremely short length scale. Is approximately 10 to the minus 33 centimeters. A very small length scale. Now, of course, notice the following thing, that we'll try to understand very carefully the physical meaning of this length scale, okay, in what comes. But notice the following thing, that this length scale is intrinsically quantum. What does it mean? It's quantum because if we take limit when h bar goes to 0, the length scale goes to 0, okay? However, the length scale can also go to 0 if we switch off gravity. So there are 2 ways to make Planck length disappear, to go to 0. One is to take h bar to 0, in other words, to take classical theory, or we can keep h bar fixed, but take g Newton to 0, switch off gravity, and again, the Planck length goes to 0 in that case. This is important to remember. This would be important when we come to validity of semi-classical description, okay? So now, since we have a Planck length, we can also define a corresponding mass, and this is called Planck mass, which we can define as h bar divided by length, because the dimensionality of h bar is length times time times energy, or since c is 1, it's length times energy, and so on, length times mass. So this is the mass scale. Or if we take this expression, right, the Planck length is square root from h g Newton, and we get that this is effectively square root from h bar divided by g Newton, okay? And so the Planck mass is a corresponding mass scale. Approximately, Planck mass is, I think it's 10 to the minus 5 or 4 grams, something like that. Or more in particle physics units, this is 10 to the 19 GeV. Now, 10 to the 19 GeV is enormous mass for particle physics. This is 19 orders of magnitude higher than mass of the proton, for example. Okay, so it's a huge mass scale. So therefore we can use instead of Newton's constant, now coming back to units of h equals 1. Now we understand what is the limit of switching off gravity. So if in units h equals 1, switching off gravity would be simply taking Planck scale to infinity, okay, which is the same as taking Newton's constant to 0. Okay, so in units where h bar is fixed, I can, and when I say gravity is weak, this means that effectively Planck mass is infinite as compared to the momentum transfer in the processes that I'm interested in, okay, or equivalently Newton's constant is 0. Okay, so therefore now for canonical normalized graviton, now writing the action for canonical normalized graviton, we absorb the Planck mass. Okay, now canonical normalized graviton, let me put hat on it. Canonical normalized graviton has dimensionality of mass, and so it couples two energy momentum tensors by the power suppression of Planck mass. So here we have energy momentum tensors of all possible types. Okay. Now, energy momentum tensor, of course, has dimensionality of density, of energy density. So this is mass to the fourth. Dimensionality here is mass to the fourth, and correspondingly, H has dimensionality of mass. So dimensionality of H, canonical normalized, is of course mass. And so H mu divided by m Planck is dimensionless. Okay. So in other words, to remember is that H, the classic, so the metric perturbation, eta classical quantum, dimensionless metric perturbation, translates in terms of a canonically normalized graviton field or its expectation value. Of course, expectation value of graviton field has the same dimensionality as the graviton field, through 1 over m Planck. Okay. So therefore, let me put here arrow, because both sides could be either classical or quantum. This is simply about normalization. Okay. All right. So now we have this. Relations. And okay. So now let's go further, and now let's discuss. So already from this fact that canonically normalized graviton field or graviton quantum interacts with the separation of 1 over m Planck to a source, this is the key property of how to build a fully nonlinear gravity. Because the way we can build fully nonlinear gravity is that we can couple graviton to the energy momentum tensor, including the energy momentum tensor of its own, order by order, okay, in nonlinearities. Now, also this parametrization is useful because order in nonlinearities appears as order in 1 over m Planck. So now each nonlinear order can be mapped to an order in 1 over m Planck, and that's also useful. Okay. So now this procedure, this is known, okay, that this procedure effectively allows us to reconstruct Einstein gravity, order by order in nonlinearities. Okay, I'm not going to do it, of course, because we don't need this for this lecture. For example, first nonlinear coupling of graviton comes from coupling graviton to its own energy momentum tensor evaluated at the linear order. Okay, so in linear theory, I can evaluate energy momentum tensor of graviton and then couple graviton to its own energy momentum tensor. Now, the energy momentum tensor of graviton already at linear order is extremely complicated, and I mean, of course, I can present it. You can find it in many textbooks, but it's not terribly informative for our purposes. But what is important is the structure. So we'll just keep track of the structure. So the structure of graviton coupling, for example, to the first nonlinear order, the the graviton couples schematically. Of course, this is schematic because there are different contractions of indices with all possible contractions and derivatives. But the important thing is that it's a qubit self-interaction, okay, trilinear. So it's a trilinear self-interaction with 2 derivatives, okay? So it contains 2 derivatives, and let me parameterize it like this. 2 derivatives, 2 powers of graviton, these are canonically normalized, and then there is, of course, separation by 1 over m Planck. So in other words, there is an effective coupling that you can think of it here, effective coupling, effective trilinear coupling of gravity, okay, which is given by by derivative divided by m Planck. Now, in general, so we can have interaction among n gravitons, and the typical structure is that each higher order interaction adds a power of 1 over m Planck. For example, we can have 1 over m Planck in power n and d square h square. Okay. So now now we can, so now we are in a position to define a quantum coupling of graviton, okay? Quantum coupling. Why? Because difference between Planck mass and Newton's constant, and difference between Planck length and Newton's constant, as we said, is the reason why Planck mass enters here. And of course, in units h bar equals 1, it's the same thing. You can trade Planck mass for Newton's constant, but there is h bar there, okay? Planck mass is a quantum object, like Planck length, as we said. Newton's constant is not. Newton's constant doesn't contain any powers of h bar. So the quantum coupling, so it's customary to define a 4-point coupling of 4-point interaction as a reference point, okay? So this is true not just in gravity, it's true in general. So four graviton vertex, okay? So graviton, 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 graviton vertex. And we can call this alpha gravity, okay? In analogy with electromagnetic coupling, for example, okay? And so this coupling, what is important is that this coupling scales as you can see very easily. We have 2 derivatives and 2 powers of m Planck. So effectively what this coupling, the way this coupling scales is momentum transfer in the process divided the Planck square, okay? So this is momentum transfer. Okay. So now this is very important. So let me a little bit elaborate on this. Okay. So what, of course, very often we use this language. We say high energies. Okay. However, what matters for making gravitational interaction strong is not a center of mass energy, but is the momentum transfer. In other words, is the momentum really that flows through the coupling of graviton, okay? So that's what probes the strength of gravitational interaction, the strength of gravitational coupling, okay? Not the overall energy. For example, we can have a star has humongous energy, but star is not probing strong quantum gravity regime, okay? So unless star is of the Planck size, okay, then of course it's not a star. Okay, so this is the important thing to remember. And so now we can understand now when gravity enters in the strong coupling regime, because now we have all the ingredients. So we have canonical normalized gravity, canonical normalized graviton, and quantum coupling of canonical normalized graviton. And perturbative expansion in this quantum coupling breaks down when quantum coupling becomes order 1, okay? So we cross into a strong coupling regime where, when? Well, we see that, so for momentum transfer approaching the Planck mass, alpha gravity becomes order 1 and breakdown of perturbation theory in series of alpha gravity. Okay, so therefore, as long as we are dealing with processes, okay, in which the momentum transfer between individual gravitons is much less than the Planck mass within Einstein gravity. Now we go into modifications, but within Einstein gravity, we are in reasonably good perturbative regime in expansions in alpha gravity. However, of course, there is a caveat here, because this is true as long as I'm considering, so this helps me enormously as long as I'm considering quantum processes at 3 level, okay? Because, for example, if I'm considering process in which I have gravitons, let's say, I don't know, 2 gravitons going into many, as long as the momentum transfer per vertex is small, we can perfectly nicely treat this perturbatively. There is a caveat in the following sense, however, that if the number of legs in the diagram, even if the diagram is tree-level, if the number of legs is too high, the number of Feynman diagrams grows factorially. And there is another sort of breakdown of perturbation theory, which has nothing to do with strong coupling. This we should remember, okay? So therefore, what I want to just you to remember is that the fact that coupling is weak doesn't guarantee you that perturbation theory is valid, because perturbation theory can also break down because of collective effects, because of multiplicity of Feynman diagrams, okay? But as long as that doesn't happen, that happens to very high orders. But as long as that doesn't happen, we can do perturbation theory, okay, in alpha. However, of course, the moment we start considering loops, we need to do something about loops, because the reason is that the virtual gravitons that flow, the momentum of virtual gravitons flowing in the loops can be arbitrarily high, okay? Because there is no kinematic restriction on virtual gravitons, okay, on the momenta of virtual gravitons. And I mean, there are some kinematic restrictions, but the momenta of virtual gravitons can be arbitrarily high. So because of this, the loops are cutoff sensitive of gravity. And we'll come back to this discussion when we discuss sensitivity to the cutoff, okay? But this is something to remember, okay? Are there any questions so far? Okay, I don't hear any questions. So yeah, let me then continue a little bit before we make a break. We still have time.
Perhaps, yeah, can you say some more words on this thing of the large N, the fact that the number of Feynman diagrams grows factorially with?
Yeah, sure. So yeah, sure. So now, by the way, this phenomena is not specific to gravity. Actually, in gravity, it works upside down in certain sense. So this is a general phenomena. For example, even let's take theory. I don't know. Let's take phi to the fourth theory. Okay. So a scalar theory with phi to the fourth interaction. Okay. So with coupling alpha. And suppose I'm looking for some process. Let's say it's at very high, sufficiently high center of mass energy. Let's say I'm looking for a process in which I take two phis into many, okay? So we have diagrams like this. Yeah, okay. Now, what happens is the following, that this process, this is, let's say here we have some, let's say here we have like, I don't know, n final legs. And so the process scales as number of vertices, right? And so the scaling goes like as alpha in power n. And if alpha is small, so let's take alpha to be arbitrarily small. Now, if alpha is small, this creates an impression that the perturbation theory is better and better for large n. However, the caveat is that the multiplicity of Feynman diagrams grows as factorial. So roughly for large n, the growth is like factorial. And so at the end of the day, what happens is, I mean, there are some subtleties here, of course, but at the end of the day, what happens is that the cross section of the process grows as alpha, basically it grows as alpha n factorial, okay? And so now you can see what is happening. What is happening here is that obviously sooner or later, no matter how small is alpha, sooner or later factorial wins, okay? Right? And so this creates a false impression that if I consider processes in a weakly interacting theory, so let's take alpha to be minuscule, I don't know, whatever you want. In the weakly, no matter how weak is the interaction of the theory, if we increase center of mass energy sufficiently so that we can produce many quanta, sooner or later the cross section will saturate unitarity. Okay, so this is now This is a false impression. And the reason is the following. First of all, as you can see from this expression, the cross-section not only saturates unitarity, it would naively violate unitarity. This cannot happen, obviously. Okay. Now, the caveat here is the following, that this, we have to think in terms of expansion in N, and then we can think in the following way. So if I think of this cross-section as expansion in N, this expansion is valid as long as the high order, and as long as N to the N plus 1 power is less than N. Okay. As soon as the next order term, seemingly next order term, becomes as important as the previous order, this expansion breaks down. And now we can see very easily that actually this happens at to the nth order, given approximately by 1 over alpha. Okay, so I call it this point as a point of optimal truncation. So in other words, the point of optimal truncation is that if you have a weakly interacting theory, the perturbation theory in alpha in the 3-level processes is perfectly fine as long as you don't go above N1 over alpha. So here it's ideal. Okay, so perturbation theory. So beyond that, simply what happens is that perturbative expansion in alpha breaks down, and the series have to be resummed. And actually, there is very interesting physics here. There are different methods like resurgence and so on. So here, the series have to be resummed, and whenever you do that carefully, you see that, of course, there is no growth of cross section. Everything is perfectly fine. Okay.
See, but I have a question here, because this is I understand that if you're fixing the number of external legs, you can you can say, okay, I can trust the result only up to this N. However,
Right.
this thing will also enter in loops. Now in gravity,
Yes, exactly.
in gravity, you say there is a cutoff, and you will discuss this later, I guess.
Yes.
But
Exactly.
in other theories, do these loops pose a problem?
Of course, it's the same thing, because remember, so this, I think I mentioned it in the first lecture.
Mm-hmm.
So, for example, this type of growth of multiplicity of Feynman diagrams is precisely the reason why the perturbative loop expansion, why the perturbation theory are asymptotic series, and they are not really convergent. That's precisely the point. So we have exactly the same breakdown of loop expansion at the loop order, which is given by above 1 over alpha. So that's why we can only trust naive perturbative loop expansion only up to loop order 1 over alpha. So beyond that, we have to do exactly the same in loops. We have to resum. So this particular fact that the breakdown of perturbation theory, whenever we have either large number of final or initial particles or large number of particles floating in the loops, that's a generic feature of quantum field theory. Yeah, so that's why perturbative series are not really convergent. I mean, that's why they are asymptotic series. That's why we say that they are asymptotic series. Now, of course, this is not a concern, because if you have a valid theory, which is UV complete and etc., the resummation is always works. And after correct resummation, we can see that the higher orders are suppressed. Now so for example, there is this whole, it's an extremely interesting field of physics. I mean, field of, for example, resurgence. People are doing these resummation approaches to this resummation, different approaches to resummation. Now, what I wanted to say is that gravity, there is a caveat in gravity, because in gravity, what happens is that a certain set of diagrams in gravity are well behaved. They are better behaved than in ordinary, for example, in phi to the 4th. And the reason is the following, that since, for example, imagine I want to look for a process in which I distribute. for example, you look for the process in which two gravitons go into many. Okay, some process like that. And so, sure, this also scales as alpha in power n. But now notice the following thing, that for the fixed center of mass energy, if I fix certain center of mass energy, and if I increase number of final legs, in certain set of diagrams, I cannot do that without lowering the momentum flow per vertex.
So alpha decreases.
Exactly, and this decreases alpha because alpha gravity depends as a power law on the momentum transfer. And correspondingly, alpha gravity for those loop diagrams is much better behaved than it would be behaved for lambda phi to the fourth theory, for example.
This is generic of effective field theories, that the perturbative expansion is better in this sense.
Yes, you can say like that. Yeah, you can say. I mean, in gravity, literally, because it's a power dependence. It's not logarithmic dependence on the momentum transfer. It's a power dependence. So the gravitational coupling runs as a power law for the scale, and that's why for the set of diagrams is better behaved. Of course, this doesn't apply to all diagrams because I mean, obviously, we know this Weinberg's infrared theorems, etc. That's a different story. Okay, so this is basically the point.
Thanks a lot. Perfect.
Okay, thank you. Are there any other questions? Because I think it's better to take questions and then make a break because we are approaching the. Okay, Omar has a question. Yes.
So it was just about the same topic. So in, let's say, the limit where you have many external lengths, is it related to what you said about high occupation number of the field? Because in some way, it's like going into a limit where the occupation number is very high. So maybe in this diagram, you wrote about two theories and the line that connects them, two theories with different degrees of freedom, and there is like a border. So this many external leg diagram is in some way trying to cross this limit of high occupation number. Yes, exactly, and it goes like into a classical limit, and the degrees of freedom change. So the question in a precise way is this related?
Absolutely.
Is it related to that?
Exactly, that is related. That's an absolutely correct comment. That's a very good comment. Actually, for example, to make even a shortcut. Of course, I'm not going to discuss this in these lectures, but actually, our group and other groups, we have been showing that, for example, in the language of amplitudes, if you want to understand black hole formation, actually it turns out that the amplitudes are given precisely by two gravitons into many. Okay. The amplitudes that correctly capture formation of black hole as a quantum process. Okay, so the high occupation number, in final state, these type of diagrams, you can think of them as describing production of a classical object. Okay, in the high energy collision. Now, production of a classical object in high energy collision. In weakly interacting theory must be exponentially suppressed. Usually it's exponentially suppressed. There are exceptions, like for example, black holes. And the reason black holes are exception because black holes, they carry entropy, very high degeneracy of microstates, and that compensates for this suppression. But in general, yes, for example, in lambda phi to the fourth theory, you can understand precisely the suppression of many legs, producing many legs, as the fact that theory in that regime describes production of a classical object in quantum collision, and that is exponentially suppressed. Of course, that requires a correct resummation. Once you do correct resummation, you see that it is the answer is exponentially suppressed. So that's an absolutely correct comment. Yeah. Is there anything else before we make a break? Okay, if there's nothing else, we can make a 10 minutes break. Sorry that I forgot break yesterday, but okay, today I'm not forgetting it. All right, so.
Okay. Well, 10 minutes, when do we reconnect here?
Yeah, 10 minutes, I don't know, let's say we reconnect literally like in 10 minutes.
Okay.
Now, let's Are we back? I assume you can hear me.
Yeah, perfectly.
Okay, very good. So now let's come back to the story with black holes. Okay, so let's view black holes from this perspective. What we just understood about Einstein gravity as an effective field theory from bottom up, right? So the first thing we noticed, remember, we noticed the following thing, that the expansion in around the source is expansion in g Newton times the mass of the source, or which is the same thing, the gravitational radius of the source, which is mass times g Newton, or which is the same thing as mass of the source divided by Planck mass squared. Okay, and so the expansion in nonlinearities is expansion in Rg over R, okay, for source. And so what we can already anticipate that linear theory stops to be a good description once the distance from the source approaches the gravitational radius of the source. Okay, so the signal for this is that first, non-canonically normalized graviton field. Okay, so this becomes order 1. Okay, because remember H00 was H00 was of order Rg over R. And so in the language of a canonically normalized graviton, this means that canonically normalized graviton field becomes of order m Planck. Okay. So in other words, approaching the Schwarzschild radius, gravitational radius of a given source, so the way theory tells us at the linearized level that we are close to gravitational radius of the source is that canonically normalized graviton becomes of order the Planck mass. Okay. So at this point, we can understand that all nonlinearities are equally important. But by the way, these you can also see from the famous fully nonlinear Schwarzschild solution, right? So the interval for Schwarzschild solution is written in spherical coordinates. Let me remind you that this is just this is well-known expression. Where this is the usual story, the theta square plus sine theta square d phi square. So this is the interval, right? This is the interval for fully nonlinear Schwarzschild solution. Already this tells you, so this is basically H00 written in spherical coordinates. And so fully nonlinear solution also tells you tells us the same thing. Okay, so that's why we have so the way in geometric description theory tells us that nonlinearities are important is that it forms a horizon. Okay, so basically the horizon at the distance of gravitational radius Rg is a way a geometric theory tells us in geometric language that nonlinearities became equally important. Okay, but in the language of effective field theory and quantum field theory, this means that nonlinear interactions of canonically normalized gravitons become equally important. Indeed, right? So we said that typically we can parameterize like this, right? Nonlinear interactions of gravitons. So we have two derivatives, two powers of canonically normalized graviton. Okay, and then each 1 over m Planck, each power of h bar, so each power of h, canonically normalized graviton is accompanied by 1 over m Planck. And it is clear that once h becomes of order of order m Planck, either in classical language or in quantum language expectation value, all the nonlinear terms become equally important. Okay. However, the fact that nonlinear terms become equally important, this tells us that we have to take into account nonlinearities. The series in RG over R expansion, they have to be resummed. Okay. But the terms are still terribly small. Why? Because of derivatives. So in other words, derivative of graviton field, if Rg, the gravitational radius of a object, for example, a black hole, is much larger than the Planck length, okay, or which is the same thing as 1 over m Planck. So if gravitational radius is much larger, then nonlinearities, although they are equally important, they are still much smaller compared to the Planck scale because of derivatives. So in other words, the way in the standard classical GR we understand that from the fact that the tidal forces, for example, if black hole is large, at the horizon, tidal forces are not noticeable. For example, right now, you can say that all of us, we are crossing, or we are near the horizon of a black hole of the size of our universe, because if you calculate if you do the following exercise, if you take the Hubble radius of the universe, this is Hubble, and if you calculate the entire mass within the Hubble radius, cosmological Hubble radius of the universe, and then calculate gravitational radius, so Hubble radius, let's call it H inverse, and if we calculate that mass and then calculate a gravitational radius of that mass, we'll get it to be very close to Hubble. For the flat universe, it's exactly Hubble. So gravitational radius of the universe is the same as the Hubble radius. Okay. So from that point of view, of course, universe is a cosmological solution. It also has a horizon. It's not really a black hole. I'm just saying if the mass inside the Hubble is sufficient to form a black hole, and so yeah, you can say that we are crossing horizon of a gigantic black hole of the mass of the universe, but we are not noticing it locally, and the reason is precisely that the gravitational radius of the universe is enormously larger than the Planck length, and correspondingly all effects of the derivatives of canonical normalized graviton are negligible. Why? Because each derivative brings 1 over r factor. Okay, so if you are around Schwarzschild radius, then around Schwarzschild it would bring 1 over rg factor, and if rg is much larger than the Planck length, derivative is suppressed compared to the Planck density. Okay. So therefore, what the important lesson is that if object is fuzzy and large and gravitational radius of the object is large, the object is not probing a strong coupling domain of gravity. It is probing a strong field but weak coupling. Now, field is strong because the canonical normalized graviton, so strong field, because canonical normalized graviton or its expectation value is of order m Planck. But the coupling is weak. The coupling is weak because first, nonlinearities are much smaller than Planck density. So h over m Planck in power n derivative is much less than Planck density. Okay. And or equivalently, gravitational coupling alpha is much less than 1. The typical gravitational coupling, if I'm dealing with a, let's say, an object which is of the size of its own gravitational radius, let's say a black hole or something near a black hole, corresponding alpha gravity, if I think of gravitational field as collection of canonically normalized gravitons, the coupling among those gravitons, individual gravitons, the coupling among those gravitons would go as 1 over m Planck square times Rg square. And this is a minuscule coupling. So for example, to just get a feeling, let's take a black hole of the centimeter size, okay, of the Earth mass. A black hole of the Earth mass would have centimeter size, okay. And so alpha gravity in that case would be, m Planck is 10 to the minus 33 centimeters. So alpha gravity would be 10 to the minus 66. This is essentially 0. Okay. Now, the reason why gravitational effect, nevertheless, of the gravitation of the black hole of 1 centimeter size at its Schwarzschild radius is strong because of the collective effect, because the occupation number of gravitons in order to compose that kind of gravitational field is enormous. Actually, occupation number of gravitons is precisely 1 over alpha gravity for a black hole. So, and so this would be like 10 to the 66. Okay. Okay, so any questions about this so far? Okay, so I don't see any questions. So therefore, let's move on. So why are black holes important? And why are they also important for beyond the standard model physics? Of course, black holes are important because they exist and we know that, and they are fascinating. But they are also very important for beyond the standard model physics. Okay, so there are several reasons for that. First, they are, as we will discuss, black holes are very good indicators of the validity of the theory. Okay. But before going there, black holes represent a boundary between the world of elementary particles and world of classical objects, or in particular black holes. Okay, so let's try to understand that. Okay, let's imagine that we have imagine that we take a particle. So let us take a particle of mass m. Okay, so let's take a particle of mass m, and let's ask the following question: what are the characteristic scales, length scales of this particle? Okay, the length scales. So there is a length scale. First length scale is Compton. So there is Compton wavelength. Let me call it LC, which is inverse of the mass. Okay. So now, what is the physical meaning of Compton wavelength? Okay. For example, physical meaning of Compton wavelength is this: if I take a particle and I localize it within its Compton wavelength, of course, the Compton wavelength is not a size of a particle, because elementary particle has de Broglie wavelength, which also tells us about localization radius, etc. So Compton wavelength is not size. We can take particle and localize it within its Compton wavelength. For example, photon has infinite Compton wavelength, but I can put a photon in the box. No problem with that. Okay. So now the point is that the physical, one way to think of the physical significance of Compton wavelength is that if once we approach a particle at a distance comparable to Compton, okay, Compton wavelength, the energy of quantum fluctuations becomes comparable to the mass of a particle. Okay. So, for example, if particle is localized within its Compton wavelength, the most of the energy of a particle, because of the localization, is coming from quantum fluctuations or momentum of the particle, and is not coming from the mass. Okay. So the Compton wavelength is quantum because it's an intrinsically quantum wavelength, right? So there is a second wavelength. So without gravity, if I have a particle of mass m, it has these characteristics, a Compton wavelength of this particle. And I know roughly when quantum fluctuations become important for accounting, for example, for the contributing into the energy of a particle. Now, gravity brings two new length scales. So gravity brings, of course, it brings Planck length. Planck length is not a characteristic of a particle. It's just a general length scale that gravity brings. Okay. Now, as we already discussed, Planck length or Planck mass, why they are important in gravity, because they tell us when gravity becomes strongly interacting, strongly coupled. So in other words, remember we discussed in the first lecture about validity of degrees of freedom. So up until the momentum transfer of Planck mass, graviton represents a good quantum degree of freedom. It's weakly interacting. But beyond that domain, graviton can no longer be trusted as a good degree of freedom. So what happens to graviton above the Planck mass, for the momentum transfer above Planck mass, is very similar to what happens to pions above momentum transfer of order the QCD scale. They stop to be good degrees of freedom. And so we have to do something with the theory. We have to UV complete theory. Okay, so the picture here is, so here we have gravitons. Okay, and here domain that requires UV completion. All right. So here is a boundary where alpha gravity becomes order 1, and this corresponds to momentum transfer of order Planck length, Planck mass. Okay. All right. So this is universal, but also gravity also endows. It gives as an endowment to any arbitrary particle of mass m a new length scale. So particle characteristic length, which is gravitational radius of a particle. So now we have gravitational radius, which is mass of a particle divided by Planck mass squared. Again, of course, I'm ignoring factors of 2 and stuff. Okay, so now there is this characteristic. Now, gravitational radius is a classical radius. Doesn't contain any powers of h bar because what enters is simply Newton's coupling. Okay, so it's a classical radius. Okay, very good. So now we have the following picture. Let's plot something here. So let's say here we have mass of a particle, right? And so what happens is that with increasing mass, the Compton wavelength decreases, right? So we can plot it like this. Okay, so this is L Compton. Then we have Schwarzschild radius, which is linear in M. Okay, so this is 1/m. And then we have a gravitational radius, which is linear Rg, which is m/m Planck square. And gravitational radius increases. There is a crossover, and actually A crossover is at the Planck mass. Very interesting. So let's see, what are we learning from here? Okay. So if a particle is much lighter than the Planck mass, okay, so if we are in this domain, here it's a domain of elementary particles. So gravitational radius is irrelevant because Compton wavelength is the dominant radius for this type of particles. Gravitational radius is fictitious, okay? It is there, you can formally define gravitational radius of an electron, but that's not a real scale because that's not a real scale as far as structure of the electron is concerned. Of course, that's a real scale as long as far as gravitational interaction of the electron is concerned. Of course, the electron interacts gravitationally, but now I'm talking about a substructure of the object. So gravitational radius of the electron doesn't affect a substructure of the electron. Okay, there is nothing that it brings. Compton wavelength is more important. So here, therefore, we can talk about elementary particles. So in this domain, in the domain where particles are much lighter than the Planck mass, most elementary objects are elementary particles. Okay. Now, now let's try to crank up the mass of an elementary particle. So the mass increases, and so Compton wavelength decreases, and gravitational radius increases. At some point they meet, and then they depart. And so in this domain, most elementary objects here, most elementary objects are black holes. Most elementary, meaning most compact, let's call it most compact objects are black holes. So in this domain, there is nothing, there is no meaning. For example, we cannot call an object of mass m larger than the Planck mass an elementary particle because such an object cannot be localized even to its Compton radius, okay, Compton wavelength, because it will have first to cross its gravitational radius. So correspondingly, this is a domain of objects that among these objects, the most compact objects are classical objects. There is nothing more elementary than black holes. So it's like we have two worlds, the world of black holes as most elementary objects and world of elementary particles. And the separation happens at the Planck mass. So Planck mass, therefore, has a very interesting meaning. That's a boundary between the world of elementary particles and world of black holes. So we can write it like this, Planck mass. So here we have black holes, and here we have particles. Okay. In particular, there is no elementary particle of the mass heavier than the Planck mass in any theory with Einstein gravity. Okay. Now this will have important this simple fact. Of course, this is simple, but highly profound. This fact. This has important consequences for defining one of the most interesting puzzles of the standard model, the hierarchy problem. Okay, because this what we are learning from here is that gravity sets an absolute cutoff on the mass of any elementary particle. This cutoff has nothing to do with perturbation theory. It's fully non-perturbative. It's independent of how we resum the series, how we compute loops, etc., etc. So the non-perturbative non-perturbative cutoff is provided by the Planck mass. Okay, any questions about what I said so far?
If me,
Yes, sure.
can you Can you explain why there appears non-perturbative cutoff?
Say it again. Could you repeat the question?
Can you say again why at mass of Planck scale then there appears non-perturbative cutoff?
Well, yeah, because again, so let's reflect on this again, right? So the gravitational radius of an object of an object, right? So here's an object, right? So this object has some mass m, all right? And so there's a corresponding gravitational radius given by, okay, twice mg Newton, but doesn't matter, 2 doesn't matter. There is a gravitational radius of the order of mass of the object divided by m Planck square. Now, this object that we have, it could be extended or could be compact, right? So, in other words, the distribution, for example, think about the wave packet, okay? So you can produce a wave packet in a theory with gravity. This wave packet could be outside of its gravitational radius, okay, or within its gravitational radius. So let's say Earth, okay? So let's take Earth. Earth has a mass which is much higher than the Planck mass, obviously. But Earth is an extended object which is extended beyond its gravitational radius. Okay, so here is the gravitational radius. This is gravitational radius of an object, okay? And this is an actual radius, okay? Now, for this type of objects that have size, that have extent beyond their gravitational radius, okay, essentially gravity is weakly in a weakly interacting effective theory at the size of the object, okay? So because, as we said, if we have an observer here that is measuring gravitational field, or for example, this observer can measure all possible invariants of Einstein gravity, okay? So all possible invariants can be measured. These invariants never reach the Planck scale, okay? So for the extended objects. So for example, this is what is happening in the Earth. In the Earth, none of the curvature invariants are even remotely close to the Planck scale, okay, to the Planck mass. So gravity, for all the practical purposes, for describing gravitating objects such as Earth, gravity is in the weakly interacting region, okay? It's in weak field and weak coupling. So for such objects, we are weak field because the field reaches, and this is much less than 1, but also weak coupling, okay? Because alpha gravity is much less than 1. Now imagine that I want to understand and ask the following question. What is the most elementary object of this mass that I can have, okay? Right? So this is an extended object beyond this gravitational radius. Okay, now let's ask the following question. Can I have for example, Earth, let's take Earth, right? So Earth is not elementary, we know that. It consists of many quanta, all right? And it's also described very well by some classical solution. But we can ask this question, why can't I have an elementary particle with the mass of the Earth? What's the problem? Why can't I introduce a particle, hypothetical, let's say beyond the standard model, and I introduce a particle, hypothetical particle, with the mass of the Earth. Now, without gravity, there's no problem to do that. Without gravity, if gravity is not there, we can postulate that there is a particle beyond the standard model with the mass equal to the mass of the Earth. There is no fundamental principle that forbids us to do that. But with gravity, that is not possible. Because if such a particle would exist, it can only be called elementary if we can localize it within its own Schwarzschild radius, within its own Compton wavelength. But that's not possible, because localized within its own Compton wavelength, before it has any chance to be localized within its Compton wavelength, it has to be localized within its Schwarzschild radius. And correspondingly, it will simply be a 1 centimeter black hole. Okay, so there will be no way in effective low energy theory to distinguish such a particle from a black hole of 1 centimeter gravitational radius. Okay, and this reasoning has nothing to do with perturbation theory. It's just the Compton wavelength is not a perturbative notion. Okay, and gravitational radius is not a perturbative notion. Perturbative notion is an expansion in this parameter or in this parameter. But none of these statements that what I just said, that if you have a particle which is heavier than which is has the gravitational radius, and you localize it within its gravitational radius, that it becomes that the expansion for this expansion for the particle will break down. That's a non-perturbative statement. Okay, so that's why. Does this answer the question?
Thank you.
Okay.
Yes.
No, yes, please don't hesitate to ask me, because of course these are important concepts, and I want this to be very clear. Okay, is there anything else about this along these lines?
Yes, sorry, one question.
Yes.
So from your reasoning, what you're saying is that it's not that it's impossible to have it, but that it would be indistinguishable from a black hole.
Well, yeah, but then you yes, sure. I mean, if you yeah, you can say like that. Of course, in physics, whenever something walks like something else and looks like something else, then yeah, we just call it that name. So yeah, that's what for all the practical purposes, so there are two aspects. Okay, so one is that it would be indistinguishable from a black hole of that radius semi-classically, but that's not most important. More important thing is that it will be a classical object, because any object that produces a gravitational field, okay, with occupation number of gravitons much larger than 1, cannot be considered elementary anymore. Okay, so that's basically that's the way you can think about it. Okay, so you can, for example, you can forget about black holes even and say, okay, I have this elementary particle, it produces a gravitational field. All right, let me roughly count what's the occupation number of gravitons in that field. Okay, so occupation number of gravitons, I mean, so I have a particle, let's say, right, and this produces a gravitational field around it, and this gravitational field has self-energy. Okay, so there are certain number of so now you can ask the following question. Let me think of this gravitational field as a certain quantum state of gravitons. Okay, and let me count number of those gravitons that contribute most into the gravitational self-energy. And so you can see very easily that that number for any object that has mass larger than Planck mass is larger than 1. So that's why any object heavier than the Planck mass produces a classical gravitational field. Okay, produces a gravitational field which is classical at the wavelength that is most important contribution to the gravitational self-energy. Okay, so we can do this exercise. For instance, do the following thing. Suppose I have, even in Newtonian gravity, very crudely. Okay, let's take a particle of mass m, and we said this particle produces a Newtonian field or component of H00. Okay, so let's call it Newtonian, and so Newtonian field is what is Rg over R, right? And this is a canonical normalized field divided by the Planck mass, right? Okay, so this is canonical normalized field. So canonical normalized field goes as m Planck Rg over R, right? So now this field, this is sort of a canonical normalized gravitational field. And now this gravitational field contributes into the gravitational self-energy. Roughly contributes something like this, okay? Something like this, okay? So the gravitational self-energy. And okay, so now we can ask the following question. If I have an object that is smeared at some radius r, I don't know, we can smear it at some radius r, R capital. So this is an object smeared at some radius r. It produces a profile of the gravitational field of this type, okay? So you can ask the following question. Let me think of this this field as being composed of gravitons. Of course, these are not real gravitons. They are not on shell. They are not propagating. But you can estimate what's the dominant wavelength that contributes into the gravitational self-energy into this. Okay, this is self-energy density, and then there will be self-energy d3x. Okay, and so there is a dominant wavelength. Dominant wavelength is of order the smearing of the object. For example, if I think of object as a uniform sphere, okay, so the dominant wavelength that contributes into gravitational self-energy is of the order of the size of the radius of the sphere. Okay, so you know now what is the contribution to the gravitational self-energy, and you know what is the canonical normalized graviton field, and you can now translate this into the occupation number of the graviton field, and you will discover it's easy to see that the occupation number and will roughly go as mass of the object divided by m Planck square. Okay, so this will be the occupation number, and the dominant wavelength that contributes into the gravitational self-energy is R. Now, this immediately tells you that this is a very good measure for classicality of the field, and this immediately tells you that the mass, if mass of a distribution is much larger than the Planck mass, the corresponding field, you cannot treat it as a quantum. There is no way at the wavelength that contributes into the gravitational self-energy. Okay.
Okay.
Now, of course, the electron also produces classical gravitational field at large distances. But here the question is to single out those constituents of the field that contribute predominantly into the gravitational self-energy of the system. Okay, so this is discussion about those constituents that have characteristic wavelengths comparable with the size of an object. For example, if we do the same exercise for an electron, it's useful to do that. The electron of Compton wavelength, this Compton wavelength, and if we ask what is the contribution of gravitons of this wavelength into the gravitational self-energy, is negligible. Actually, occupation number of gravitons of this wavelength is negligible. So that's why electron, despite the fact that at long distances, of course, gravitational field of the electron is classical, electron is not a classical object. Okay.
Mm-hmm.
But that's not true as soon as we have an object which is heavier than the Planck mass. Okay.
Yeah. Okay. Perfect. Thank you.
Okay. Okay. So now let's go back and now let's recall a few. So let me now discuss two things. So one is, so again, this of course is not course in gravity. Obviously, I would go into much more details. And also, this is not a course on black holes, obviously. But I'm just trying to, the way I'm structuring the lecture is to give as much information about black holes and gravity as we need for understanding beyond the standard model physics, and also for understanding how gravity can solve why gravity is very important in defining those puzzles and perhaps answering some of those puzzles. Okay, so this is the important thing. So I'm just trying to give you a minimal possible information that we'll need later. And so for that, I have to recall a few properties. First of all, define two things. First, define semi-classical limit rigorously, okay, and then recall black hole properties of semi-classical black holes. So, semi-classical limit. So semi-classical limit is a limit in which we can ignore back reaction. Okay, so this is a limit of zero back reaction. So in other words, let's consider a particle placed in a gravitational field. So here we have T mu nu. This produces gravitational field H mu nu, and then we have a probe here, tau mu nu. So tau mu nu is moving in the gravitational field produced by T mu nu, by a probe. Now, tau mu nu, we are interested in the situation when tau mu nu is a quantum particle. Okay, so there is a quantum particle moving in the background gravitational field. Now, of course, since nothing is classical in nature, the source T mu nu, as well as the gravitational field that it produces, at the end of the day, they are quantum states. However, and because of this, they experience a quantum back reaction from a particle that moves in the background gravitational field. Despite this fact, okay, there is a well-defined limit in which this back reaction can be completely ignored. Okay, so what is this back reaction limit? The limit is when we want to be still in quantum theory. So h bar is 1. We don't do anything with h bar. Okay, so quantum effects, we want them, quantum effects about this object tau mu nu, a particle, probe particle. We want quantum effects to be there, but we want to switch off back reaction. So therefore, in this limit, what we can do, so that let's say this is source of mass m. Let's take it as a source of mass. So what we can do is that we can take the limit in which h bar is 1, but we take Newton's constant to 0. However, we want to keep geometry non-trivial, and correspondingly, we have to take m to infinity. Okay, so in such a way that we keep gravitational radius fixed. Gravitational radius, we keep it fixed. So in other words, we are taking double scaling limit in which gravity is infinitely weak, the source is infinitely heavy, and gravitational radius is and geometry is finite. So in this limit. Now in this limit, there is no back reaction to the gravitational field from any particular probe particle of finite mass. So any probe particle of finite energy or finite mass produces a zero gravitational back reaction, and correspondingly, this limit is cleanly a zero back reaction limit. In other words, in this limit, we can consider physics of these probe particles in a background geometry without worrying about back reaction to geometry. Right? Okay, I hope this is clear. So this is the strict semi-classical limit. Now, of course, as you can see, we have to pay the price. Of course, this limit also corresponds to the same thing equivalently, since G Newton goes to 0 and Planck goes to infinity, obviously. Okay, or which is the same thing as L Planck goes to 0. So this is equivalent to this, right? And so in this limit, there is a zero back reaction from particles. Now, the best understanding of black hole physics, and actually exact understanding of black hole, some of the aspects of black hole physics, is in this limit. Okay, So in this limit, we know that black holes, they they are subjected to important quantum effects, okay? And in particular, they evaporate by Hawking radiation. So in this limit, we have finite size black hole, okay? RG is finite, right? Finite size black hole. And so in this limit, we can consistently analyze a probe, what happens to a probe quantum field, including graviton itself. Okay, we can, for example, consider graviton in the background of this metric, or a scalar particle or a photon. What happens to these particles in this background? And so what happens is that there is a production of particles, okay, which has some very interesting properties. So the production is such that the spectrum produced is thermal, and therefore it's featureless. So there is a Hawking temperature, which is given by the inverse size, okay, of a black hole. Again, I'm ignoring 4 pi's and stuff. And the spectrum is thermal. So in other words, in this limit, what happens is that black hole represents an infinite capacity reservoir that produces particles with thermal rate and thermal spectrum. Okay. So correspondingly, there are few features. For example, thermal production of particles with this spectrum means that if you have certain particle species, okay, in the theory, all the species are produced with an equal rate. So emitted energy, so the derivative of the mass, time derivative of the mass, is given by the temperature square times the number of species. Okay, because the particle species, they just produce in a democratic way with equal rate. Okay. Now, despite the fact that derivative is non-zero, the black hole mass in this limit doesn't decrease. So, okay, so this is very important to be very precise about these limits. So, despite the fact that black hole evaporates, since we already took the limit when the mass was infinite, black hole represents an infinite reservoir of infinite capacity reservoir. So the lifetime of a black hole is infinite, and back reaction is 0. Correspondingly, black hole radius in this limit doesn't change. Okay, so just black hole radius is fixed, the mass is infinite, and it produces particles with unlimited rate. Okay, with unlimited time with a fixed rate. So this is like a Stefan Boltzmann law for evaporation of a black hole in this business. Now in this limit, the black holes are very well understood. Correspondingly, we can extrapolate from this limit and extrapolate certain features of black holes reliably, even for finite mass black holes. Okay, so in other words, for example, if mass is finite but large, so we know that these features should approximately be correct. Okay, so therefore we know that even for finite mass, as long as mass is much larger than the Planck mass, if we are within the validity of Einstein gravity as an effective field theory, these features of a black hole should be approximately valid. Okay, so the corrections, for example, corrections to thermality, corrections to thermal spectrum, corrections to the evaporation law should be small. Okay, let me see the time scale. Okay, we have 5 minutes left. Now, why is this important? Because this, for example, already this fact is a very good indicator whether we are within the validity of effective field theory of gravity. Because, for example, suppose you have a theory, and in your theory, you discover that corrections to these laws are not negligible. Okay, so for example, you all of a sudden you discover that the black hole in this theory simply can no longer, if you assume this type of thermal evaporation, you will get a contradiction. Okay, we'll encounter this in the next lecture. Okay, now this is a very powerful tool for understanding that this is a signal that we are beyond the validity of effective field theory. So somehow, by deforming the theory, if we cannot maintain these properties of a black hole, this means that we have also affected gravity. And we have to look for a correct completion of the theory. So because of this, black holes are very interesting and very powerful indicators when we cross the validity of effective field theoretic description of Einstein gravity. Okay? In other words, black holes are a good indicator when they're telling us that we are beyond the cutoff, okay, of the theory. So another property, and I'll finish today's discussion with this, another property of a black hole, the extremely important property, is that they carry entropy. They have huge microstate degeneracy. They carry entropy. Of course, for entropy, we have to consider finite mass, because entropy of a black hole, this so-called Bekenstein-Hawking entropy of a black hole, goes as black hole mass divided by Planck scale squared, which you can also translate as the area in units of Newton's constant. Okay, there is also a factor of 4 here, but so area is of course proportional to Rg square in 3+1 dimensions. Or you can write it as an area in units of Planck length squared. So now the fact that entropy, the black holes carry this entropy, actually it turns out that this entropy is what I remember I mentioned about black hole production in high energy collisions, etc. This entropy is what makes it very robust. Then in high energy processes, black holes are usually the result of the evolution. Okay, so for example, if you collide particles of very high center of mass energy, if the impact parameter is less than the gravitational radius of a black hole, the end result is that we produce a black hole. Okay, in order to understand this, okay, the entropy is important. So black holes carry enormous entropy, okay, which is, however, notice the following thing, that in the semi-classical limit, in this limit, sorry, entropy is infinite. So we cannot take simultaneously semi-classical limit of a strict semi-classical limit of a black hole and keep entropy finite. Entropy is an intrinsically quantum notion because it's about degeneracy of microstates. And this is very good because entropy is one indication that tells us that once we make the mass of the black hole finite, there will be corrections to this, for example, laws of thermality and evaporation, which will be controlled by the inverse powers of entropy. Okay, but we should postpone for the next discussion. Okay, I finish here today's lecture.
Okay, so we are right on time. Thank you, Gia. Exactly at 11. If there are urgent questions, otherwise we a very urgent question. And that's why
today we don't have discussion session. So yeah. and there is immediately there is a next lecture because schedule is very tight.
So apparently there is no hand raised. So
am I allowed a very quick question? Just did I understand correctly, Gia, that So we understand gravity at energies lower than the mass, the Planck mass, but also at very high energy, eventually we will produce black holes which asymptote to this semi-classical limit. So we somehow, the part that is missing in understanding a UV completion of gravity is right next to the Planck scale, where we don't know, where we might produce black holes, but we don't know how they behave.
Exactly, that's precisely the point. Yeah, absolutely. So now, of course, this discussion goes beyond my lectures, because I didn't want to enter there, because these are the lectures on beyond the standard model. So I'm just giving minimal information about black holes. I'm not putting any new exotica or something. But you are absolutely right. So the fact that in high energy collisions, usually we end up with black holes, it represents a very strong indication that probably ultra Planckian gravity is safe. So in other words, in ultra Planckian domain, black holes unitarize the scattering processes in gravity. And the remaining point where indeed we don't know what to do is this point of Planck mass, here.
Yeah, around there.
So this is the point where we don't know what to do, because there both perturbative expansions break down. We cannot use expansion in 1 over entropy. We cannot use its expansion in alpha. And so perhaps that's the price to pay. So we need some more powerful tools to understand gravity around the Planck scale. So most difficult place for gravity is the Planck scale. Yeah.
Okay. Thank you very much.
You are absolutely right. Yes. Thank you very much for that question. Yes.